Hi there everyone, and welcome to another TouchDesigner tutorial. Today we're going to take a look at an algorithm called Convex Hull and make a simple TouchDesigner implementation of it. A convex hull is a way of finding the outer boundary of a collection of points. I've been using it lots in my recent organic simulation projects as a way of creating a defined boundary around a sometimes diffuse set of points. One way to think about the technique is to imagine placing a set of pins into a board, stretching an elastic band around them, and then when you let go, the band contracts around the outermost points. The shape it creates is the convex hull. So no matter how complicated this arrangement of points is, the convex hull gives us a simple shape that contains all of them. In this video, we're going to build our own slightly hacky version of a convex hull in TouchDesigner. Instead of implementing traditional convex hull algorithms, we can approximate the idea using a combination of the neighbor and analyze pops. By looking at how points relate to a bounding shape, we can create a sort of responsive mesh that forms itself around all of the points. The resulting system is a simple and effective way of achieving convex style effects in both 2D and 3D. Let's begin. We're going to start this network off with two objects. The first is going to be a point generator, and this is going to be the set of points that will build our convex hull around. I'm going to start out working in a 2D plane to have a more simple visual for this, but then we can scale this up to work in 3D as well. So I'll stick on a circle, so it's 2D, and I'm going to put my number of points down to 1000. I'm going to bring in a null and a noise, because we don't want to draw a hull around something that's super boring. We're going to make this kind of displaced in an interesting way. And because we're working in 2D right now on that output tab, I'm just going to say p.xy, just so we are scaling our noise in 2D. So the next thing we need to do is we need to create a hull that we can draw around this object. And because we're working in 2D, I'm going to start with a circle. I'm going to bring that out into a null as well. And what I want to do in the circle is I want to up my divisions to something like 200. So it's quite detailed. If we open up our side viewer and go into Geo View, we can see our two objects here. And in a bit, we'll look at how to scale the circle to actually match around this for that starting value as well. So I'm going to add in a transform here. But before we do that, let's get into the part where we build our convex hull approximation and wrap this around these points. The first thing that I want to do is I want to use a neighbor. And I'm going to bring in the points I want to wrap my hull around into the second inlet. So important here that we have this in the top inlet and this in the bottom. Then in neighbor, I'm going to go ahead and turn off neighbors and num neighbors, and I'll turn the max neighbors down to 1, which is the lowest value it can be. The distribution I want to switch to closest. And to make sure that we can create a calculation between these two sets of values, which have different lengths, I'm going to bring down this drop down and I'm going to select P, which will create an attribute called neighbor P. Let's take a look at that in a chop. And what we want to look at is neighbor P and P. So we can see these are the positions of where the neighbors attach. And what we can see is if I tweak this max neighbors distance, we see that the neighbor points change in terms of their proximity. And this is going to be useful for calculating the difference between the neighboring points to the points in our hull. So basically we can calculate if things are close or far away. And for now, let's just bring this out into a null, so we can view the end of our chain as well as the points that we're going to wrap around. And the next step, and really the final step, is to bring in a math mix. And what we want to start out by doing is we want to calculate the direction between these 2 points. So I'll do A minus B, and I'll do neighbor P minus P, and I'll call this hull dir. I'm going to bring this into a value where I can multiply hull dir to scale it. And right now I'll keep that at 1. We can tweak that later. And finally, we're going to do a plus b operation. So p plus hull dir. And we can see that right now it's formed to the points, but maybe not quite in the way that we want. So you can play around here and maneuver this structure. So let's go for a value of 2. And we can already see that it's done a pretty good job of sort of encapsulating those points in that hull. Let's go ahead to the transform and move that around a little bit with an abs time dot seconds times 0.2. And we can see that this hull is already quite well aligned. We can try changing this down, so let's do a smaller hull size, so 40, even 12. So you can experiment with bringing this up or down to have a more or less granular line. This also can be brought really far down and sort of made into a sort of a square, but be aware that it's not going to be able to morph completely to your set of points in this instance, the way that we're mapping this. So let's bring this up again. Let's keep it at 30. I quite like the more angular vibe. Okay, so this is pretty good. One thing we can notice here as well is that the transform has an effect on this. So I actually had scaled this up already. So let's just take this noise off and take a look at the transform. So by default, that uniform scale is going to be 1. And what we can see here is that circle is within the points. And because of the way that we're doing this system, we really want the circle to start off outside of the points. So it essentially gets pulled in and morphs to it. So we can see that the scale of that initial circle is very important. If it's too big, we're not going to have anything. And if it's too small, it's going to map within a more central set of points. So having it bigger than the points is very, very important. And what I'm going to do is I'm going to show you a super useful way of doing this automatically using the Analyze pop. Let's bring out this point cloud that we're going to draw the hull around to a Analyze pop. In the Analyze pop, we have access to all kinds of information. If I bring this into a chop, we can see average, centroid, maximum, minimum, etc. I want to use centroid and size. Now we have access to the centroid and size values. We could just go ahead and reference from this chop into our transform. But what I'm going to show you is something a little bit more advanced, but can be really useful in terms of just having a few less conversions between domains. So right now we're converting from pop to chop. And even though it's not using that much computational power to do this, it's a really nice trick to know to be able to take this analyze data and directly bring that into here. And I'm going to go ahead and delete this chop so we can start with a blank slate here. And just to remind ourselves, we're looking for centroid and size. If we take a quick look at the information on our analyze pop, we can see we're outputting 1 point, 1 primitive, etc. So basically the size of our point array here is 1, and this contains 2 attributes which contain the centroid and the size, both of which are float 3. So this is really useful to know. In terms of referencing, we first want to do the regular thing, so do op analyze 1, close that up. And what we want to do is access that point class. So what I'm going to do is say point, open bracket, again in quotes, we're going to say size, and we can check here to see that we're writing this correctly. So that's size with a capital S, 0, and then we'll close that up. If we just write this, we're not going to get any value coming through. And that's because we can see here that it has a float 3 values. So it has 3 values packed into that attribute. So to access the first index, we can do 0. And that's going to change the centroid for the X. For the Y, let's go for 1. You can see it's a little bit different. And for the Z, let's do that too. Right now we're not working in 3D, but it's useful to have, so we can see that that sticks at 0. And I'm also noticing another mistake here, which is that this should be centroid versus size. This should be the central position of all of these points that's calculated by the analyze. Okay, so now that's correct. And we can see that we have values for our X and our Y. Right now, no Z, so it's just going to keep that at 0. I want to put this uniform scale back down to 1 so that our scaling from the analyze is going to be correct and not doubled. And what we can do is, we can copy this and just replace centroid with size. In the interest of getting this into our muscle memory, I'm going to write this again. So op analyze 1 to reference the analyze pop dot point open brackets. Now we're going to put in our size attribute and make sure to have a capital S 0. And remember, if we end it there, it's not going to do anything. So bring in our 0. And let's see what we've done here that is wrong. Okay, there we go. 1 and 2. One thing we can see is it sometimes gets pulled into this central point in the middle, and it kind of ends up missing out a big chunk of points. So what I also do here is I divide by 2 to make sure that's going to hug the outside much better. If we go and look at the pre-processed version, we can see that that circle, which we're later using as our bounding hull, is sort of moving around those points pretty well. You can again go in and tweak it up a little bit if you want. So you could go and just kind of give it that little bit extra depth. You could go and do a uniform scale of 1.5. It's really up to you in just terms of how you kind of tweak and kind of finalize that little bit. But this section in general gives you a fairly good approximation of an object that's going to bound all of your points. And then you can use your technique for creating the hull. Okay, so let's save this up. This is the 2D version. I'll just call this hull 2D, and we're going to change this so it works in 3D. And it's really not any effort at all here. So let's just take this circle, let's make that into a sphere. And we can see right now we have our sphere points, maybe a little diffuse there. So let's tweak that period up to 5. And let's go ahead and make a few more points. And what we can see is our bounding is trying to move around that, but it's not quite succeeding. And this is because we're working again with a 2D plane here. Let's bring in a sphere pop. And I'm going to view this as lines. And let's bring that in. So now we have a hull that is moving around that position in 3D. So really, you can just switch in and out between 2D and 3D. Let's turn down that detailing. You can see having this less detailed is going to give you something that doesn't quite bound all those points. Again, you could play with things like your bounding to make this larger. Keep in mind that this might move things too far away, because remember, we're working with that neighbor to track that proximity here. So I find having something that's, maybe like 3 in terms of the frequency if you're working with geodesic will do a pretty good job. What I finally want to show you is how to work with objects that aren't just amorphous shapes being altered by noise. So we're going to work with this bust. What I do want to do before loading this in is I want to delete some of the information here so I'm not making a crazy number of calculations in terms of distance. We don't even have to have this be super dense. We can have it be quite diffuse and thin. So let's turn on thin. Bring it down to something that looks like that. So we have a general shape. And I'm going to save this. I'm not going to plug it into the noise for now. I'll plug it in there. And let's just visualize that. So we can see that we have a pretty good approximation right there. If I was to bring this down, we can see how my frame rate is dropping quite a bit. If I was to add in things like a noise, say, to actually automate this, we can see that every frame, the calculation it has to do is quite challenging. So having in a delete that has less points, we can see that it's a little less well formed, but it pretty much does the job. And then you can just kind of put in your final object at the end because it's still bounding to that. You have enough data that you can actually see the external points. Let's try that noise in there. Obviously it's not manipulating the one underneath, so let's just have that visualizing too. You can kind of add this into your post-production. One other thing to mention here is we were working just with XY noise earlier, so let's go ahead and just delete this. So it should be now 3D noise. And we're really going to town on this shape here. So I'm going to turn down that amplitude a little bit. And it should be the same across both. Yeah. If you want to make a more detailed bounding mesh, you can turn that up or down. Right now I have it as a series of lines, but you can also have it as triangles. So it's going to actually mesh around your object, which looks pretty cool. And you could go in and color every one of these vertices if you wanted to create a more Voronoi style bounding. Let's just put this back to 2D. So I'm going to switch this to my circle, and this can be a circle as well. And again, something you can always play with are these neighbor distances to create different relationships in your image here. In the event of having a system where you can't quite get it to map over all of the points, a little hack that you can do is to bring out a surface here. And then when you render, so let's just create some render simples. And let's do a render simple for these points as well. What you could then do in post is essentially multiply. Let's make these values white for both in the diffuse, and then let's just multiply those together. So then you would have something that's constrained by your outline. And in this case, you would then do another render simple. You could either add in a line material or just do an edge and then comp these together. So this is a little hack where you can just in post-production have your final output always mapping around these points, even if the system itself isn't quite there. I hope this has been an interesting tutorial for you, and stay tuned for much more. I'm attaching the example file for Patcher subscribers and some more advanced options for component tier in my Patreon. Thanks so much for watching, and see you soon.